Ooh, a little hot. Okay. Oh, hey, my YouTube bot actually worked for once. It's a Christmas miracle. Okay. I guess we're good to go. Um, hey, BR Gaming. Oh wait, oh, I didn't even do that in thing right in the Twitch chat. Ugh. No, I did it. Oh, God. Songs. Unpin. If my hairline didn't recede, I would look like Ed Sheeran. Fuck you. It's true, but I don't need to hear that. Dude, why can I not pin this freaking? Oh my God. There. Thank you, Twitch. Okay. So, what am I doing? Oh, okay. This is actually a song in Q. Let me actually start playing. Uh, and then this is a different song. This is the wrong song. This is your song. Ooh, there we go. I think it's a decent level. Oh, I mean, you gotta be more specific then. Um, you gotta request like put lollipop and then also the name of the artist. Simple harmonic motion sucks. Yeah, PR gaming. Said the grad student office hours. Will you answer all my math? Yeah, color cone. I can answer every single one of your math questions easily too. I barely even have to think. Okay. So what's happening in this homework that I want to do is basically we have okay. Let me Oh, like this lollipop? Wow. Okay. Um, so basically for this one, we've got a bunch of data that represents, hey Kyo. We have data that represents, basically sound in the ocean, and it's mostly just background noise, but there's supposedly a submarine. After your liver has gone, you will still have peanut butter. These fortunes have been terrible. Um, it's hard to concentrate when the song is playing, to be honest. um, at the end of the month, you will gain more peace of mind. That's kind of mysterious. But yeah, so basically there's a submarine moving around in this water. We're supposed to figure out the frequency of the sound the submarine is making and filter the data so that basically only the submarine sounds is in it, and use that to like track where it is. And I believe I've done that. Um I basically found this is a plot of the Fourier transform of our data. Okay, thank God that's over. I can actually think again. Oh my God. Oh God, the thing is freaking out. Please stop. Okay. Your first soft grad question. Oh yeah, let S1 and S2 be projective smooth surfaces over an algebraically closed field of characteristic 0 if S1 is a K3 surfaces and S2 is derived equivalent to S1. Is S2 a K3 surface? Are S1 and S2 necessarily isomorphic? Yes. Next question. The proof is trivial. Um, so yeah, with this, I basically took the Fourier transform of our data, because we have 49 samples. And so I took the Fourier transform at each time, and then I added all those up, because that eliminates the noise. The noises mean 0, so Picasso. Oh God, what is that song? Let's see. There you go, color cone, perfect. Um, I lost my train of thought. What is this? I mean, that's what I'm explaining. Um, so we have this data that represents sound in the ocean. To isolate the frequency that the submarine is making, I take the Fourier transform of the data, I add it up over all the times, and that gets rid of your noise. I need to make a figure that represents that, but that'll be later. And so if you plot the the frequencies that are being made, like the sum of all these things. If you want, you can try me. But yeah, the title says that I'm taking questions too. So yeah, it's kind of weird that the frequency isn't the same in all directions. It's probably... I mean, the frequency might not be the actual frequency of the sound. That's probably why I've been getting mixed up on this. It's more to do with how the sound is changing. I mean, if it's JEE, I wouldn't bother, because I can't do those, but... Do you have a different question? Just put it there. Like, I'm not just gonna sit here doing nothing, so... I might look busy, but... Yeah, I'm not just gonna sit here, like, doing nothing, waiting for a question, so... Jed, congrats on the first. Caught him sleeping? Yeah, you did. Rex, that's probably... There's no way that's the song that you wanted. Yeah, I think you need to be more specific, because I think what it does is it just gets the first result off YouTube if you search for that. Am I allowed at my university to assist which you're not enrolled? Like, assistance from people outside the class? It kind of varies. I mean, in this class, oh, just show up to the course. Oh. They probably wouldn't notice, because no one ever takes attendance. I don't actually know if you're technically allowed to just sit in on a class, though. Well, that was like a metal song. Okay, so yeah, if you take up all the, or if you sum up all the Fourier transforms to get rid of the noise, you get two kind of blobs. And the thing to notice is that this is about -5, -2, 7. And this one down here is the same exact thing, but the signs are flipped. Because with Fourier transforms, you kind of always have that like complementary frequency that's really the same thing. I still don't really know why, like, I sort of know why it's necessary to have negative frequencies in Fourier transforms, but I still don't really know what it means. Oh yeah, I love metal. But yeah, so now that we know kind of like the frequency that the submarine is making, we can create a filter to get rid of the noise. And so what we do to do that is we take Gaussian functions and we center them. We take two of them, one centered on this one up here, the other one centered on that one down there. And basically what that does is at the center of the Gaussian, it's 1 at a maximum, and that kind of smoothly just decays to 0 the farther away you get. So what this is doing is it's keeping the signal that we actually want. that we're centering it on, and it's kind of scaling down all of the other signals, which is just noise. So before, where I had the actual just data here, the two frequencies, they're now covered up by my two Gaussians. And the next step is to actually take the signal at each time, multiply it by our filter, and then we can do the inverse transform. And oh, this is one that Rex tried to delete. I'm just going to skip it. And so yeah, after I filtered out the data and I go back to the, well, yeah, I filter the data, I do the inverse Fourier transform. We get a little animation. It doesn't run that smoothly, unfortunately. But this blob should be the submarine as it's like moving around. And actually, I should try this again, but with different parameters, just to see something. Oh. God, this library. I don't know if I like this library that's being used to plot this. It's just so slow. Um, Sounds good, Kyo. Godspeed to you. No, it's called Plotly. And it's what was used in the example, so I've been using it too. I don't know. But the thing I want to try, I want to adjust this ISO min, ISO max. Because what it does is it basically draws like level curves, but in higher dimensions, they're level surfaces. And it was just set only to draw things at 0.7, but I wanted to draw a big range so I can test how well the filter is working. Because it should look the exact same, I think, basically. Unless something went wrong with my filter. Oh, that does not look the same. We're off to a bad start. Why is it all dark blue? Clonk. You're on the verge of something big? Ooh, that's a good fortune. No, this is like a pretty good level. of heavy. Um, I feel like I'm pretty picky in general when it comes to metal, and I would say like this is just like okay in my mind, but it's definitely like not too heavy. I'm kind of like I don't really get this library. Like, why is it only drawing dark blue things and there's no yellow or pink or anything? I've kind of consistently had this problem and I don't really understand it. Must be a mountain cliff. Okay, if I wanted to do the equivalent thing with matplotlib, what would that look like? Matplotlib ISO surface, I guess. Let's just start by Googling that. Interesting. Um, hmm. I don't know if that's what I want. I don't know if I should be worried about. I don't know. I don't know if I should be worried about all this like noise that seems to still be in there. Um, if I go back to the original version of the file, I think this is unmodified from how the professor gave it to us. What if I do the same thing here just to compare how it looks? Ugh, freaking thing. It's getting there. Eventually, it's got to work. Come on. Where's the actual plot? I'm getting scammed. I think I need... Actually, stop. Stop what you're doing. Okay. Don't save. Yeah. Stop complaining. Okay, try again. We got a white bar. That's progress. Ooh. So that's definitely... This is definitely worse. Than what it looked like before the filtering. Maybe we can make the filter tighter. Bruh. Keep waiting. Ah. This freaking library. Okay, I closed this. Let's close this. Dude, please close. Dude, this is so stupid. Okay. This file is 200 megabytes. Might be weird for the 30 seconds of the song there's an intro? Okay. Good to know. Okay, so I wonder if I can save myself some heartache by not showing these other figures. And so if I want to make them smaller, I think I go 0.5. Yeah. Wait, I do want that. Okay, I think we can move forward. How do we as humans accept death knowing that one day life has to come to an end? uh... It's a good question. I don't know, it's just kind of part of life. Just like Thanos, death is inevitable. Why is this worse? Why is there more noise? It's just all part of the process. Why get out of here, bar. You're not supposed to be here. Mate, this is so slow. My computer's complaining, I can hear it. And it quit. Um... Oh my god, brother. Save. So it is the figures that take up so much memory. Oh, this code won't work. Because I need that code too. Excuse me? Actually, okay, clear all. Don't run this. Well, actually, okay, no. Let's step through it. Restart. That. There's nothing wrong with this statement. Oh, wait, yes, there is. Okay, fine. You got a point. So is this the moment where we look at how much 32 gigabytes of RAM cost? No. I do desperately need a new PC, but that's not happening anytime soon. Okay, these balls are smaller. That's what I wanted. I can just kind of see it like right there and right there. So in theory, we should be filtering the data more aggressively. So let's just try this again because these notebooks are kind of finicky. I am a little worried something got messed up with like variables not getting cleared out. Yep, small balls. Small balls are best balls. No, it still looks terrible. Hey, Yanis. That's so weird. I think there's no reason why it should look like this. There's definitely no reason why I should look like this. Hmm. Restart. Phobos. Thank you so much for the raid. I hope your material sciencing continued to material science. It really materialized at the end? Hell yeah. You'll love to hear it. Vernus here on my end. Check out Phobos. She's awesome. Does study streams, Final Fantasy streams, art streams. What more do you want? Very good at programming. We stream it all. What I'm working on today is this homework assignment for my scientific computing class. I'm currently wrestling with a Python library that wants to kill my computer. It has it out for me. But basically the idea of the assignment is we have a bunch of data representing like audio in the ocean, and we're supposed to filter that data and find this basically the frequency that a submarine is making and use that to track its path through the water. And so I'm using Fourier transforms and trying to kind of I figured out the frequency that it's making. I've created a filter, but I'm kind of messing around with that filter to try and hopefully make it work better. I need to start back from the top and step through this again, though. Does category stream count as Final Fantasy stream? I mean, I don't think there's a lot of overlap between category theory and Final Fantasy, but maybe. Who am I to say? You know what? I don't think we need this anymore. Okay, so what if I go the opposite direction with my filter? Am I right? Your bachelor thesis on category theory? Ooh, that's cool. Yeah, so, let me actually, like, this is the original kind of, like, helper file we were given in class, if it ever loads. Oh, I messed with it, though. Let me put it back to how it was. Skibbity by Little... I'm warning you, I reserve the right to skip songs. I think they've been nice to us and they're not changing the frequency. We have 49 samples at different times of this entire like three-dimensional space. And so the idea that I've confirmed with the TA is correct is the noise in the data is mean zero. So what you can do is I guess it's volume, yeah. And so the frequency that I'm measuring here isn't the actual frequency of the sound, I think. It's just I don't quite understand what the Fourier transform does in this context, but it's like it's had something to do with how much it's changing. Um, but yeah, so there's noise in the data, but it's like basically white noise with mean 0. So what you can do is, if the stream is lagging, it's me. That's annoying. Dude, why is this running like crap now? Probably because I'm streaming. Is it a bad idea to stream this more because of this? I don't know how choppy the stream is. Ooh. Okay. This is terrible. It's supposed to be showing a plot down here, but it's still thinking about it. Um, this is a library that like the professor provided in his example. I don't necessarily have to use it, but oh, I'd already skipped to the end, but ugh. Basically, if this was working right, you could see the actual like a little like blip like travel around. But I guess it's like noisy, and we still want to filter it. And so that's what I have been trying to do. Yana said, I had told back a laugh when the professor and the postdoc were telling me about this, and they said it would be about comonads. Wait, what's funny about that? I don't know if about category theory. So I'm just adjusting the parameter of my filter for like how aggressively it's filtering stuff. And so I'm going to try a less aggressive one. And see if that somehow helps. I don't imagine it would, but I just want to see what happens. How big of a volume is your samples from? I have 49 samples, but do you mean like what's the like maximum volume that was recorded? This is still bad. It's better, I guess. I don't know why that would be better. Oh, like the range. I bet I could find that. Or I guess over what? Oh wait, I guess 49 samples of time. Uh, and then 3 dimensions with 64 samples each. So 64 cubed space samples for each time. Oh, maybe I'm still, or maybe I'm still misunderstanding. You do mean the actual volume measurements. Can't type right now. Oh yeah, a monad is what people always reference when talking about functional programming category theory. It's a joke for how over the top it is, like a monad is a monoid in the category of endofunctors. Can't type right now. Imagine missing the words. So the message makes sense. Okay. Fair enough. Um, I guess I could just do like, I just want a quick like minimum maximum of the volumes. np.min subdata raw. np.max subdata raw. Ooh, it's raw. Okay. How do we get negative volume? That's weird. Let's do absolute value. Yeah, so they didn't actually say what the data is. Volume would make sense. Okay, so basically 0. The max is 1.44. Yeah, that's a file where I was just kind of playing around with the data. 1.44. They don't really tell us what the units are. um, it's just acoustics data. Broad spectrum recording. Broad spectrum. Does that mean something? Measuring those broads. I've studied a broad or two. Yeah, I don't know. So yeah, like this is basically the most that they say about the data that we're given. um, they're pretty specific with like what you should do. Uh, so determine the frequency signature generated by the submarine. I've done that, which I could actually show. Well, I did that in 2 ways. Um, and then the filter, I guess, is what I'm working on now. And then they want you to do like a projection of just the x and y coordinates, which wouldn't be too hard, I don't think. But I'm trying to understand how this filter is actually working because it's obviously like in the notebook it looks kind of weird. It is kind of fun. I want to show off the plot that this makes. Hey, Kirk. Give me one minute though. Okay, get rid of that. Get rid of that. Comment that back out. So, the first way that I tried to figure out the frequency of the submarine was by taking all the Fourier transforms, well, this is true for both ways that I did it. Take all the Fourier transforms, sum them up. That gets rid of the white noise because that's mean 0. And then to plot it, we have 64 cubed, like we have 3 dimensions, 64 samples in each dimension. So what I did is I plotted 64 different z values. So this is like each slice of the cube basically, and then x and y coordinates are just like horizontal and vertical. And so you can actually like go from left to right to go from the bottom of the cube to the top of the cube down here. And you can see the maximum ends up being wherever the background dots are darkest, because it means there's like the most kind of contrast between these and the maximum value in the middle. And so the maximum, or the frequency that is like coming up the most often is like somewhere right in there. And you can, and because of the way Fourier transforms work, there's like a complementary one. This is minus 6.91 for the z value. So over at positive 6.91, this is going to be basically the same thing. But the signs are flipped. I was doing practice problems for the national competition thingy. Had 5 hours for 5 questions. Solved 3 in just 2 hours of trying them. Ooh, nice. Huge. And so yeah, there's a little bit more of a practical way to do it, which is what I did here. Same data, taking all the Fourier transforms and summing them up over time. And then this is the same thing, but represented just in 3 dimensions, and I still don't get what values are actually being plotted in this. Yug, no, this is this is my homework, and I'm a master's student. This is not high school level. But yeah, this basically. Oh wait, the maximum is maybe at. The maximum is at 6.9. I'm a little disappointed by how slow this is running while I'm streaming, though. I could do a separate task for this. You're in uni preparation math class, haven't studied Fourier transform yet, so that checks out. Oh, yeah. I mean, Fourier transforms are really cool, but you need a lot of math before you can. Well, not necessarily if you're just applying them. If you want to understand what the Fourier transform actually is, you do need to know a lot of background math. You could start using it though without knowing why it works pretty early, I think. All right, I don't know. What I want to do right now is keep working on the filter and seeing how it affects this graph down here, but I don't think my computer can handle doing that and streaming at the same time. So what I could do instead is make a figure that I'm going to need to make anyway. Because I want to justify the idea that summing our if the data has white noise, summing them over time will eliminate the white noise on average, because the noise is mean 0, so it should cancel over many samples. You should go on tough competitions, so it's back and forth with uni math and hard high school math. That's fair, yeah. So, how do I want to do this? I guess we're just going to do this one-dimensionally. We're going to use a Gaussian bump because that's kind of what we expect our Fourier transform to look. And grid is 64. I do want to take some of the parameters. L is 10. Oh wait, well, we're doing this one-dimensionally. So I don't think we need a mesh grid. So np.xp, we want a Gaussian minus x squared how does just this look? plt.plot x data. Oh wait, it helps if I show it. Okay, we can work with this. I'm not going to show it. I mean, I want to bump up the end grid. Really? Wait, oh, why do I have 2 end grids? Okay, that's looking better. Okay. So we have just regular Gaussian bump. What I want to do is I want to maybe get 10 samples. Noisy signal. Zach, thank you so much for the raid. I hope your stream was good. Welcome in, people. Peach Tea Hate, Bit 101, hello. It's a me, Azakio. uh, what I'm working on right now is a homework assignment for my scientific computing with data class. Uh, it's kind of a cool assignment where actually let me show the actual assignment. We basically have noisy acoustic data for the ocean. There's a submarine traveling around in that ocean. We need to detect it and like plot its path. Hey, Atharv. Yeah, this is a song request day, so things are going to be the music will be a little bit all over the place. um, hey, energy. Government math jobs? Basically, yeah. So what we have is we have like this three-dimensional space that we've taken 49 recordings in over 24 hours. And this data is noisy. So the things that we need to do with this data are find out the frequency generated by the submarine through the noise. Create a filter. Like once we know the frequency that we want, create a filter to basically get rid of most of the noise. And then once we've denoised it, make like just an X and Y plot of the submarine's path. We don't care too much about the depth, I guess. Can you teach me the differential geometry necessary to understand general relativity? I only barely understand it for myself, and it would be I would have to like basically create a course for you, and I don't have the time to do that. It's kind of a lot. I have used the book I studied out the book Gravity by James Hartle. It's free on the Internet Archive, like archive.org. And so that studies general relativity through differential geometry. I wasn't the biggest fan of it though, because apparently a big thing in general relativity is also tensors, and the book doesn't get into tensors until like the end. Hey, Aditya. Yeah, it's kind of engineering-y too. Sounds tense, yeah. Recent like kernel density estimation for 2. Ooh, I don't know that term. What we're doing is we're using just we're transforming the data into Fourier space, and in Fourier space we're multiplying it by a Gaussian function centered at the frequencies that we want to keep. Oh, so yeah, maybe that is. Oh wait, yeah. So sorry, I'm jumping around too much. I was still talking to Energy about their question. Yeah, Energy, like that. It would be cool if I could teach you that. It's just that's a very big ask. I couldn't just explain it to you in an hour. We would need to like work together over a long period of time, and that's just it's not something that I'm able to really do right now. There is I don't know if they'll have one on it, but there is MIT OpenCourseware. They do have like recorded lectures and stuff too for some of their classes. You could try looking for one there. I'm not sure. Um, you know, Gaussian curvature and so on. Why math 2? I'm being. You can be as derp as you want, but we're glad to have you here. This might be a similar idea. I'm not immediately understanding what this is. It seems like a similar thing though. Okay, see ya, Adia. But yeah, so when you're in the Fourier space and you multiply it by a function, in this case, we're taking a Gaussian function, then you do the inverse transform. That's the equivalent of doing a convolution. And I'm still trying to work out why, but it was explained to us in class that you could interpret the convolution as sort of like a windowed average. And that sounds kind of like what's happening with kernel density estimation. But yeah, I'm not sure exactly. So yeah, the unfortunate bit with this homework assignment is that the library we've been used to plot things is new to me. It's called Plotly. And this library hates me and hates my computer, and it's trying to kill my computer. So it's been difficult for me to make progress on this on stream, because between streaming and trying to do animated 3D plots, my computer was kind of dying. So the stage in this that I'm at is I have a Gaussian filter created. Actually, let me back up. I step 1, determine the frequency of the submarine. I did that. It's these two kind of blips right here. They're complements of each other. Like, it's the same values, just the signs are flipped because of how Fourier space works. We got that by taking the Fourier transform of our data at each time and summing it all up. The summing part is needed to eliminate the noise. And so yeah, once we've done that, we can create a Gaussian function centered at each of those two blips. Add them up because we want to keep them both. And then we take that filter, multiply it with the data in Fourier space. Then you invert it. And then ideally, you have data that's ready to go and be plotted, but it hasn't quite worked out. Like, this isn't... It looks better if I adjust some of how it's plotted, but I feel like I should be, like, I feel like the way I have it now should be working, and it's not quite. So I'm not sure what to think of it yet. I can't really test it properly, though, because, like I said, my computer can hardly run this code and stream at the same time. For intro to general relativity, you can probably stick to the differential geometry in R4. Once you understand the local model, you just need to patch it to understand it on the manifold. Fair enough. I know it was getting pretty freaking complicated though. I mean, yeah, differential geometry gets kind of crazy quick. Makes me wonder what kind of computers they have on board. Nuclear subs? Probably good ones. You have like unlimited liquid cooling. So yeah, because I can't really make progress on this on stream, I guess, evidently, I kind of, I swapped over to creating a figure that I'm going to need to include in my report, which I think I should include, which I want to make a figure that justifies the idea of when you have white noise, which is noise with mean 0, you can just sum up a bunch of samples in order to eliminate that noise, because on average it's going to cancel. So I'm making an example, like I'm taking a clean signal, just like a Gaussian bump, because those are fun, adding noise to it, and then I'm gonna do this like noise reduction process on it to prove that it works. Most of it is just indices spaghetti notation. I got really tripped up on that. But even conceptually, there's still some kind of crazy ideas with like tangent spaces and stuff like that. Like it is like natural, but to actually like use it is still crazy. If noise is regular, it could be something you just see what's different between the noise. Yeah, so that's hopefully what the summing idea is doing. Because like in one instance, like the noise might be up, the next instant it might be down. So if you add the two samples, it'll be 0 and you get the true signal back out, or at least close to it. So we're gonna store wait, I mean, I guess I'll do time here. Num samples, or not, yeah, I guess. For I in range num samples, noisy signal colon I equals clean signal plus, now this is going to be our white noise, np dot random. How does this function? I want, okay, please, where's my documentation? Here we go. This is useless. You're not telling me the information that I want. Oh, maybe I want rand. Bruh. Fine, I'll Google it. You know, if Penn posted the VOD yet, on our last stream on Riemann surfaces, we did find the tangent space on a general manifold. Ooh, cool. In Happy Nightmares, thank you so much for the raid. I didn't realize you were streaming. What were you working on? For anyone who's here, Happy Nightmares seems to study like a little bit of everything, but including in that everything is math, but in general, just a super like interesting stream. Welcome in, people. I'm working on some scientific computing homework. We're basically processing data, like acoustic data from the ocean, because there's a submarine lurking around in it, and we're using like filtering and stuff to kind of isolate the submarine's frequency, and we're trying to like plot its path that it took. But yeah, thank you so much again. This song, it's kind of loud. We are doing song requests. Oh wait, did the queue run out? It did. Okay. So if someone wants to add in a song, go ahead. But if it's gonna be empty, I'm gonna play my own music. I hope not. Color code. I don't think it is. I am avoiding it. I do have a different homework assignment that I could work on too, but I'm kind of scared of this one. I haven't actually read it yet. This is from my asymptotic analysis class, and it's I'm a little bit scared of it, so I don't want to look at it. Oh yeah, I was looking at the documentation for Rand. Okay, can I just do this all at once? Can I? Uh, fuck it. I won't do it all at once. No, I want to at least make this plot. Uh, I don't think it'll take me that long. Maybe we can look at it after. And p.rand, we want clean signal dot size. And so this makes a random number between 0 and 1. I'm gonna scale it. Let's just say 0.2. And then I also want to make it mean 0. So if it ranges now between 0 and 0.2, I should subtract 0.1 to make it mean 0. Aha. I guess we can make this a parameter, noise amplitude. Minus noise amplitude for 2. Okay. So big AXS equals PLT dot subplot 1, 3. Good enough for me. Oops, no breakpoints. Wait, what? I don't know why that's there. Okay, AXS 0 dot plot. I guess we'll show our clean signal. AXS 0 dot set title clean signal. AXS 1 dot plot noisy signal colon. I'll just take the first one. Set title. Example noisy signal. Oh wait, you know what? Maybe we should plot multiple. Because our point is that it should cancel over time. Then AXS2. Oh wait, we need to actually do the summation idea. P dot sum noisy signal no worries. Happy nightmares. I hope your stream was good. Closing time. Thank you again for the raid. So we're doing a little IRL stream. I always get mixed up with the axis parameter. IRL study time stream? Noish. What were you studying? I think I've chosen the right axis, but I might need to choose the other one. Ooh, good luck. That's hype. We do need to average it out, so we can say over num samples. Okay, so let's see how this plot comes out. Wait, really? I need to look back at the documentation. Oh, numpy.random.rand. Ugh. Ooh, that did not work. What the hell? I forgot the legend. I know you can't see. What the plot looked like. So how to encrypt a file, feeling like a pro hacker? Hell yeah, Kyo. The filtered signal was all sorts of janky. Oh, maybe I did the wrong axis. Could that be it? I did. Okay, this one I'll show. Just give me a second to get a screenshot of it, because it's difficult for me to show this on stream directly. Oh, that's not what I wanted to show. That is the figure I was showing earlier. So on the left is the clean signal that I started with. In the middle is the signal that I added noise to myself. Well, it's 3 examples of the noisy signal. And the point is that if the noise is like positive as often as it is negative, you can add up a bunch of these samples and get something that looks like your original back out. These edges are pretty messy. And that's actually probably... That's why we need to do filtering still, I guess. So, like, just summing things up and taking the average isn't enough. But the middle is looking, like, pretty good. Okay. So this is basically the figure that I wanted to make. I could mess with the formatting a bit. It is a little, like, narrow and tall. I don't want to do that right now, though. We could make color cone happy and look at my asymptotic analysis homework. And figure out exactly how scared we should actually be. Let me bring up my textbook for that class first. Might need it. Let's make some sloppy estimates. Get rid of that. Number 1. Find a function f such that f of x is little o of x to the n as x goes to 0, but not big O of x to the n plus 1 as x goes to 0. Oh, I thought they were both little o's when I first read this. And I thought there'd be an easy answer. I also want my notebook. Maybe we should take the definitions from the book, though. It'll be easier than writing it from my notebook. Okay, here's big O. This is the big O we want. Then let's get the little o. Okay. So if it's little o of x to the n as x goes to 0, that means the function. So let's make if n equals 1, we have a line, and little o of that would be something that is like approaching 0 from below that line. But this needs to be going to 0 faster than any polynomial. So not just a line, but also a parabola, a cubic, and every higher power. So, okay. I mean, theoretically, we could do a polynomial in terms of n. What I mean, so let's look at what the second part. So if it is big O of x to the n plus 1, how's this possible? Do we need oscillations? Okay, this would be cheesy. Uh, what if f of x is x to the n plus a half? Just going right between n and n plus 1. We can test the little o by taking the limit as x goes to 0 of x to the n plus a half over x to the n, and this should equal 0 if it is. And I think that works. I mean, we have to restrict ourselves to coming from the right. We could do an absolute value though. Okay. And would this not be big O of x to the n plus 1? If one percent thing is not big O, we have to show something does not, like, it cannot exist. Which is kind of annoying. Does the book have an example of that? Hmm. I guess not. I guess the absolute value would introduce its own issues if I did that though, because if I cancel absolute value of x to the n with x to the n, there's a potential -1 floating around. Well, that's fine. Because either way, it's going to go to 0, right? Would it might not go to 0 continuously, though. Bruh. Oop. I don't know. I don't want to think too hard about that part yet. It's just in a neighborhood of 0. Real. The book definitions are for complex, but in this class we're just working with reals. I'm kind of weirded out by how do you prove something is not big O? If there is not a number delta greater than 0? Oh wait, I need definition 1.1. Maybe that's why I'm getting weirded out by it. I mean, I wonder if I did find it, because presumably x to the n plus a half. Can we show that for any fixed k, this inequality is not true? That's what we would need if my idea does work. No. That's that's why I was thinking of like doing an absolute value thing, but then that still kind of makes this limit part a bit weird. Yeah, it's just that the step here is a little bit, or sorry, I guess going from here to here is kind of annoying because there's a potential plus or minus issue. It doesn't like matter, I guess, because it'll still be going to 0. But I just wasn't sure how to express that plus or minus, I guess. I guess. Oh, I guess what you maybe do cases. That's the proper way. Or sine of x. Ooh, true. Okay, yeah, we don't need cases. I like that. Um. Oh yeah, true. Forgot that one. Okay, and so uh I guess I want to show a contradiction here. So the x to the n's can cancel. And then if x is going to 0, this is blowing up, and so this can't be true. Same idea. Oh, yeah, okay. That's fair, too. What's the symbol for contradiction? This? Yeah. Okay, yeah. Or I guess, like, unbounded. I guess it goes to positive infinity. Okay. I guess we did it. Let's get number 2. E to the minus x is little o x to the minus n. Did the music just stop? That was just a quiet part of a song. For any n greater than... Okay. As x to infinity. And get that. Well, I wonder if they would go for the limit argument. Let's do the limit thing first. Because in class we've been using limits more than the formal definition for little o. The point of this is that it's a 0 over 0 situation. And so we could L'Hopital's it. We'd have to L'Hopital's it n times. Ooh, wait. Well, that's annoying. This doesn't get simpler when you L'Hopital's. Oh, wait. We flipped this baby on its head. Don't flip babies on their head, please. Now we L'Hopital's n times. It's going to become n factorial on top, e to the x. And that goes to 0. Okay, so that's the limit way. I wonder if they would rather the epsilon delta way, though. So we're given epsilon. So we have been given that e to the minus x is less than or equal to epsilon x to the minus n. And we need to find... Well, I guess, okay, it's not delta, it's... m of epsilon. Which is basically our lower bound cutoff point for when this starts to be true. And so what this is saying is that if you have an exponential function, let me start by drawing like the, I don't know, there's probably a name for this that it's not coming to mind, but like, let's just look at like, let's call that x to the minus 2. An exponential function, it might start off higher, but eventually it's going to catch up and start decaying faster. It's that point that we want to find, I guess. And so how do we probably need to go to the power series for E. Can convert it into something that fits the definition? Really? Uh, maybe. Oh, wait. Well, maybe this isn't okay. Let's just see how this looks. We can triangle inequality that bad boy. Does it go the right way? No, it doesn't. Bruh. If the denominator doesn't vanish, the two definitions will be equivalent. Doesn't it vanish though? Isn't the point that they're going to 0? Well, yeah, they're going to 0 at infinity. And then, oh yeah, yeah, okay, it doesn't actually. Yeah. So write the epsilon delta definition limit you just computed. Oh. Um. Oh, funny. Okay, that makes the equivalence a lot more apparent. Um. Because that does directly just give us that. I still want to know the hard way, though. Like, I guess, what, does the calculation up here prove that the delta exists without having to actually find it? Okay. All right. I don't have a good idea for how to actually find the delta explicitly with what I have written, so maybe we can take that and run for now at least. I could also just ask if the limit argument is good enough. Like, just go to office hours. Give an example with brief justification of a function that is infinitely differentiable at x naught, and yet it is not limit of its Taylor series for x not equal to x naught, arbitrarily close to x naught. Okay, this has been a very confusing thing in the class. A Taylor series doesn't have to converge. I thought they did have to converge, or else it's not considered a Taylor series. Your favorite. The function doesn't vanish. I thought they always had to, but as I've been learning in this class, they don't. Like, my first thought is something funky, like sine of 1 over x at 0. But I don't... Is that differentiable at 0, though? I don't... It doesn't exist at 0, so... Yeah. Need to have seen it once for having the idea. Well, there's an example we looked at in class. Uh... It's tempting to say yes. I think I want to think about it, though. God, I have so many notes for this class. Where's the thing I was thinking of? Okay, so we were given an example of a function. Well, this is a slightly different context, but we looked at an example function in class. Like that. And you can expand it with the asymptotic sequence just like this, which would be a Taylor series. Shit, can you? This is an example of function. This is we're looking at this because it's oh wait. Yeah, it's big O of x, but f prime is not big O of 1. So this is an example of like how derivatives don't play nice with big O notation. This one looks annoying. It is a little complicated. Also, as x goes to 0 from the right. The 0 that vanishes with infinite order, but the function is not 0. My my mind is telling me x to the x. I don't know why though. What is x to the x at 0? It's not defined at 0, is it? I keep doing things that aren't defined. Yeah, never mind. That's not it. It's not what I want. Infinitely differentiable at x naught, yet it is not the limit of its Taylor series. Okay, I think I get why you're saying that, color cone, because we need to make sure the coefficients of the Taylor series uh like don't decay, don't converge. Or I guess it could converge to the wrong thing. Never mind. Or like we could also make it just converge to the wrong, and that's probably what you're saying instead. Make it converge to something else. Yeah. Oh, ooh. I mean, maybe minusing e to the minus x squared. Yeah. No? Yeah. I, that's what I thought was the good thing. Uh, I guess that converges though. Never mind. That's a legit Taylor series. Hmm. Stone Ranger says very close also. Hmm. Shared a book you ordered. Let's see. Hey, boss dad. uh, I see Grothendieck, so I'm not surprised. That's a wild way to spell Chebyshev. Maybe it's... Well, wouldn't it be e to the 1 over x? ln x work as x goes to 1, Ayush? ln x has a... Oh, well, ln 1 minus x is a Taylor series. It's about all the inequalities. Good luck. This is... I'm sure these get really crazy really quick. Boss said, wait, I don't know if I already replied to you, but if I didn't, I'm doing well. Just kind of struggling through homework. How about you? I think you can find a Taylor series for LNX, Ayush. Oh, wait, so something like this, maybe the minus, maybe not. Yes, we do want the minus. So as x goes to 0, you'll be balk. Oh, sounds good. As x goes to 0, this gets large from the right, which means this will go to 0. Uni starts back up for the new year in 3 weeks. Final year, then you're done. Nice. JC, happy new year to you too. Good luck with your final year, boss Ted. What are you studying? Oh, so an element of Taylor series for x not equal to x naught. I didn't even read that right. Civil engineering. Focusing on fluid mechanics for my final year. Ooh, very cool. Hey, Mr. Not So Normal. This is a past calculus. This is something called asymptotic analysis, which relies heavily on calculus, but it's like a level beyond it. This is for like a graduate level math class that I'm in. We're learning all sorts of disturbing things like Taylor series don't have to converge or something like that. I'm still not completely clear on it. If you want to talk about calculus though, or you have a question about it, please do ask me. Peak Twitch content, hell yeah. Welcome in, Very MOSFET. Yeah. Oop, sorry, that was really loud in the mic. I'm sorry about that. Yeah, like this is early into it, and it's not that out there for if you've gone through like your typical first year calculus stuff. No, that's not a bad guess though. It is the New California Republic from Fallout, if you've played those games or watched the TV show. So it's one bear with two heads. Wait, why would this be? This isn't defined at x equals 0. Thank you, thank you. I don't want to go there, Desson. It's from a video game. So wait, did I make did I not make the same mistake again? Like this can't be it because it's not defined at x equals 0. That's kind of funky. Be prepared to accept a wondrous opportunity in the days ahead. Ooh. That's not the right window. Like, I think... This wouldn't be addressing the actual issue, but... minus 1 over x squared. I mean... This is a removable discontinuity. You think you're gonna find a job if you don't fall from the mountain cliff? Yeah. I think that's the idea. Because that derivative definitely exists. If we found, I found the murder, hell yeah. And so the point, I guess maybe let's just take one derivative and investigate it at 0 just to kind of justify the infinitely differentiable piece a bit. E to the minus 1 over x squared times 1 over 2 over x cubed, right? I still don't know how to take derivatives. Okay, yeah. In the limit of that as x goes to 0, is still 0, because this thing is going to decay faster than that blows up. Oh yeah, Zone. That's a good point. It's only ever going to be an exponential times some rational function. Okay. That's noise. Oh, sorry. Color cone. You don't have the same color name, but they're close enough that I got them mixed up. And so that's the first, I guess, like, infinitely differentiable. I haven't done infinitely, but this is close enough. Not the limit of its Taylor series part. When x isn't 0. Hey, Mosquito. Oh. Oh. I see. So, okay. I don't remember that from Avatar. Okay, so the point is that this numerator is always 0. So this Taylor series is always 0. And the function, it's very small, but it's not quite 0 when x isn't 0. Neat. Oh god, Mosquito, I'm very terrible at those types of questions. I'm sorry. Song requests. Oh yeah, people stopped requesting songs, so I went back to my playlist. But if people won't want to put things in queue, I'll go back to it. A normal D derivative gets hit with a hammer on the head to make partial differential symbol. Please beware of this abuse every time you write the partial symbol. Normal derivative gets hit. It's a good cause. Very MOSFET. You can do some function crafting with that function to build some smooth bump function. Oh. Yeah, like you could do like 1 minus e to the minus 1 over x squared as like a basic thing. Oh yeah, we were talking about this one. This is the one that's differentiable everywhere, right? Even though it has this like discontinuity. Gold, smooth functions. Yep. Hope you're doing well. What do you think about Cauchy derivative approximation formula? Could you have done it using that just to be fancy? Cauchy derivative approximation formula. Something that is zero outside of a closed interval. Derivatives exist everywhere. Wait, Cauchy's... Oh, is this what you mean? Cauchy's an integral formula for derivatives? We're working in real numbers, but maybe that wouldn't be a big issue. It's not holomorphic. Cauchy's out here or forming calc theorems. His name is all over complex analysis, especially. It's not holomorphic. I'm just gonna believe you. I don't feel like thinking. Mosquito, that one I can do. Derivative, cosine 1 over sine x. Cosine x over 1 plus sine x prime. Holomorphic Charizard? Hell yeah. Okay, so Mosquito, to take a derivative of this thing, you need the quotient rule. And I remember the quotient rule with a mnemonic, I think it's called. It's going to sound crazy, but I'll explain it. Low D high minus high D low. And it just like kind of flows off the tongue for me, so it's easy for me to remember it. But what it means is low means denominator, so 1 plus sine x. D high means derivative of the numerator, so negative sine x, because that's what cosine x becomes, minus high cosine x, D low, derivative of the denominator, which is cosine x. And then the mnemonic doesn't cover the next part, which is low squared. The X to be complex, you get an essential singularity at 0. Interesting. Oh yeah, makes sense. Big D energy. But functions cannot be holomorphic because they violate the isolated zero theorem. Okay. A white tier 1. You live your life, I guess. Okay, and so now we just need to simplify this. This is basically the answer here, but we can clean it up. We get minus sine x minus sine squared x minus cosine squared x over 1 plus sine x squared. And I'm noticing a Pythagorean identity here because sine squared plus cosine squared is 1. So if you have minus and minus, it's -1. Minus sine x minus 1 over 1 plus sine x squared. And there's one more thing we can do, which is factoring out that minus sign, and we get a nice little cancellation. So this cancels with one of those, so we get -1 over 1 plus sine x. So yeah, Mosquito, let me know if you have any questions about that. Would I know something given by Cauchy is just Cauchy-Schwarz inequality? Yep. And standard Cauchy function satisfying function rule? Yeah, Cauchy had his fingers in many pies. That was kind of unexpected. Yeah. This example function why we cannot have nice things in the smooth category. Okay, so let's see a question from you, Mosquito, about that. I'm going to go back to doing problems for my homework. This one looks a little lengthier, number 4. Okay. Suppose that mu is a continuous parameter and that for each mu in 0, 1, we have f of z mu is big O g of z mu as z goes to z naught from d. The proof of proposition 1.3 in the textbook suggests it might be true that if integrals exist in the Riemann sense for all z close enough to z naught, then the integral from 0 to 1 of f is big O of the integral of the absolute value of g. Since the integrals can be approximated by Riemann sums. Under what additional hypotheses on f of z mu and g of z mu can the proof of proposition... Well, okay, we need to grab this proposition. Got a proposition for you. Tired, boss? Sorry to hear that. Ah, page break. Gotta take 2 screenshots. What is this? Too veiny. I haven't heard a question described as veiny. Okay. What do they call the alphabet in Arkansas? The impossible dream? That's just rude. Oh, maybe Ayush. All my fortune cookies by far have been rude and pessimistic. Yeah. No refunds. I guess that one wasn't rude towards you unless you happen to be in Arkansas. Actually, no, you're not in Arkansas, so. Yeah. um, I like this phrasing for a question. Can you find a counterexample? No. Hmm. Oh, I mean, that's probably more pain than it's worth than Ayush. Hmm. Oh, wait, we should look at the proof. So the proof starts right here. First note, triangle inequality. Sure. That's true, Ayush. It's one of the problems that I want to solve, though, because they sound annoying. They want us to give the condition for that to hold for Riemann sums? I guess so. Hey, these sums are finite. I guess the integral is finite also. Hmm. Okay, so they triangle inequality. Oh no, they didn't triangle inequality anything. They're just using the definition of big O. Don't we need the biggest K sub n? Well, I guess we're using them all. Oh, okay, yeah, we are getting the biggest one. Uh, the basics, Dessen. It's just like the intuition of them. I still don't know them well enough. So this proof is pretty straightforward. This proof here, yeah. With the exercise statement. Where are you? Sasha. That is that. Okay. Um. Oh. Uh. There. Where's being approximated by Riemann sums? Okay. I mean, let me just look at the definition of Riemann sum. It's probably a good starting place. It's from Wikipedia. So we are assuming they're Riemann integrable. Too much theory? Oh, this is my theory class, so... Earlier in the stream we were doing some coding data analysis stuff. Hmm. I'm from America. Of course, they're going to be dense as well. Hmm. Oh, wait, no. It's mu sub I star. Not gradient. Oh my, not box. Delta. Don't read everything you believe. that's just a terrible fortune. I mean, we can't just estimate these. We need to upper bound them. So we can define Darboux. We just need to define our mu sub I star properly. Actually, these are z's. Z is still a real number, confusingly, but... Dude, I can't draw triangles, I don't know why. I guess like that is how we could define our mu sub I stars. So we have a strict upper bound. We could also do a strict lower... no, we want upper bounds. Probably. Okay, so... what does this do for us? So I am mixing up my letters. Um, Hilbert module? I have no clue. Okay, ooh, would we want a lower bound G, actually? How does this work? We know that F is less than or equal to some constant K times G of Z mu as Z goes to Z naught. It scares me too. So just it might be true. Huh. Read more books than YouTube. Picked up a calc book, was reading the Riemann sum, got completely stuck. So when do they actually use the triangle inequality that they start by stating? Maybe I don't understand this proof. We already know that this is big O of this sum. Why is it K sub n? Or wait, no, that's the conclusion. Oops. Oh, okay. We start by knowing f sub n is big O of g sub n individually. So we start with this inequality, and we can sum it up for capital N many values. That's what's happening in this step. But KB, and then, so yeah, K sub, we need to take the maximum of K sub N. It's a sequence of functions. We know individually f sub n is big O of g sub n. And the point of this proposition is to prove that for a finite sum, like a finite sum of f is big O of a finite sum of g. If f sub n is big O of g, then g dominates f. Yeah. Or at least is equal to, if not dominates. Okay, so the thing that we have... Oh, okay, so I'm starting with integrals, and I should not be. That's where I'm getting mixed up. Okay. So what we can do, we need to start from this statement here and work our way up to an integral. So I think the first thing... we can get rid of the absolute value on the left. We want the absolute value on the right, and we can't get rid of that anyway. We can multiply each side by some... We can just make it uniform. I don't think that's really a big deal. Some delta mu. And then we can sum each side. How does this work, though? Like, what do we want to sum this by? The uniform part is the big deal. Destin, the weird thing with asymptotics is that you don't care about n going to infinity often. You actually like with like a regular like Taylor series like you learn about in a calculus class, you let n go to infinity to get a better and better approximation. But with asymptotics, for whatever reason, we keep a fixed n and we vary x instead, basically. K depends on mu. We just use the fact the integrals preserve inequality. So should I write k sub mu? Mu star outer measure? I don't know. If f is less than g, then int f is less than int g. I think so. I'm not clear why k depends on mu. K comes from varying z. Hey, Cold Gold. This is the question here. Like, well, the thing I want to do next is just take a sum of each side, and I'm trying to work out what the upper bound for the sum must be in terms of delta mu. Condition on big O is pointwise on mu? I don't really know what that means. Well, I guess, like, yeah, we're holding mu fixed, I guess, for this big O definition. Hmm. Maybe Cold Gold? I'm not sure. Like f z mu, this big O of g mu means that for each mu fixed. Oh. Okay, yeah, it might involve mu, is what you're saying. Okay. That makes sense. In the finite case, we could just take the max of those k mu's. Yeah. Okay. I don't know. This is a weird one. This is the question storm. Hmm. Okay, so we actually did do an example in class that I forgot about until now. Um, in class we did do an example uh that was basically absolute value of sine is big O of just sine. But as x goes to infinity. The integral of 0 to x absolute value is not big O of integral 0 to x. I need a dummy variable, but who cares? Yeah, I'm working on a master's in applied math. I started it in August. But actually, this example doesn't help with this. Hey, Sockno. Because this specifically states absolute value. Never mind. Thank you, Storm. Never mind. I haven't really looked at the hint yet. We could do that. E to the minus L. When we make the idea the question is hinting at is to start with this statement, use the definition of big O and try to make it look like a Riemann sum, and then make that Riemann sum like go to infinity, which would make it continuous. So basically, from a discrete Riemann sum to a continuous integral is a continuous case. For L equals 0, 1, 0, comma 1, not like an interval. Z goes to 0. Z greater than 0. These are weird conditions. U equals Z over mu. Essentially, yeah, but with big O's and absolute value of G. Okay, so if mu is 0, u is infinity? And if mu is 1, u is z. Probably. We're supposed to figure it out, though. No, it's Mewtwo? True, Skirtle. Meow. True, yeah. Math genius. Uh... Sounds good, Storm. Thanks for saying hi. It's good to see you. What am I supposed to do with this? Oh, I can turn the song request back on since there's thing in queue now. Oh yeah, Destin threw in Smooth Criminal. I forgot about that. Why is it so loud? Sorry. The volume just randomly got reset for no reason. Okay, it'll be Smooth Criminal and then Energies. Jeez. Yeah. Okay. Sorry, I'm just like deep in thought on this question. I can also feel my brain just like slowing down. As z goes to 0, z is greater than 0. Hmm. I'm warning you now, there's no way in hell I'm getting through the queue already. I'm not going to be shooting for that much longer. What am I supposed to be doing with this? If L equals 0, what happens? This becomes 1. I doubt that's integrable. I don't know what to do with that. Wait, I don't know what I'm talking about. What kind of crack am I smoking? That's z to the minus 1. This one is the one where c becomes 1. I don't know what to do with either of these. I don't know how the hint's supposed to help us. Z to the positive 1? I sure do, thank you. Yeah, I don't know what to do with the hint. I think I need to work on other parts of the problem first. You scribe some estimate that seems to work if f and g are uniformly continuous in both variables. I don't think you need Riemann sum. Really? Huh. I feel like we're intended to do it with Riemann sums, though, because they're asking us to adapt the proof for continuous cases. Hmm. Hey, famished. So basically like showing Kate does not depend on Mew. Watching the pit. Ooh, nice, nice. That makes sense, color code? So... No, this is not the last question. I'm not working this homework out all today, though. There's, 7 questions in total. And I think the first few were just kind of gimmies. But I'm already running out of thinking energy. So I'm gonna have to take a break pretty soon. Oh, I much prefer grad maths. Ayush. High school math I thought was pretty boring until I took a calculus class. Yeah, my bad, Skirtle. And maybe it's a little bit low. I normally have it slightly louder, the music. Is he saying fuck me like you used to? It's a good song, though. Is that a good level? Oh, okay. So next is my class starting next week? Yeah, it's a good idea. So... supposed to consider Z going to 0? This is just 0, though. This one is something. Well, this one is unbounded. Hide again, sock now. I assume we need to find some G that these things are big O of? As Z... I don't know, man. This doesn't have Z in it. Like on the inside. And it's what's on the inside that counts. We did do a change of variables. I don't know. Oops. Keep tapping my microphone, sorry. I think I lied to myself thinking I'm in good shape mathematically until I started grad. I mean, there's always someone who's better at you than in math. Like, no matter how much you can spend your entire lifetime studying math, and there'll be someone who's doing some type of math that you would struggle with still. You think your estimate works? Okay. Got tasting this controversial linguistically, but mathematically it is true that ranked choice voting and popular voting are the same. I hadn't heard that. Sure, energy. So an epsilon you can't get rid of. So talking, I feel like I've heard the opposite, that ranked choice voting, it doesn't solve everything with popular votes, but it does improve certain things. Hopefully it's not too loud. I can't find the volume button because YouTube short suck. That's okay. What does this camera work? This guy's moving everywhere. I don't know. I mean, yeah, I don't know enough about like quantum. I don't know anything about quantum gravity. I barely know anything about the classical gravity that he's referring to, as in like general relativity, I assume. And he's saying that there's some third thing that he doesn't really explain. Because it's a YouTube short and you can't possibly explain something that hard in a YouTube short. Um, I would imagine whatever his idea is probably pretty like fringe, but I don't know. I mean, I don't really know what that means. Energy, like, how would space be emergent from substances? Where would the substances be if there is no space? Like, I don't know what that like premise means. And even then, like, I guess like laws maybe they're more abstract, but I don't know. I don't know. If you have a popular vote system, the only difference between the two is the management was just linguistic battle between people and social battle. If you're talking about the pure math, it's the same. For candidate X and candidate Y on population A to Z, both have the same effect as a ranked choice. Well, with only two candidates, they're definitely the same, but... Or wait, sorry, that's not what you're saying. I'm not quite sure what you're saying with that second comment. Um, the point of rank choice is to stop the spoiler effect, though. Or like where people feel like they have to vote for a front runner. Like I don't know how that part is debatable. Like people are more free to like vote their minds as a point of rank choice. Philosophy of space and time, which to my understanding about significant theoretical physics trees, I'm interested to learn more about it. Yeah, that's fair. I've only barely studied physics is my problem. So like I don't know quantum anything. I barely know general relativity. And I know basically nothing about the philosophy of it all, so that's why I have a hard time saying much of anything about that. Oh yeah, Daisy is always waiting. Today might have been a repo day, actually. I don't know if it's going to actually happen, though. It is? Oh. It's good to know. I don't... I'm going to wrap up the stream soon anyway. Princess... Yep, that's me. No, I mean, I was planning to wrap up the stream soon anyway. In Alejandro's channel, we're watching some quantum mechanicals. Not bad, a lot of relabeling in physics from known math objects. Linear algebra are functional. Yeah, it'd be cool to learn quantum stuff. Yeah, I've been told that linear algebra is a pretty big thing. Get noms. Yeah, I do kind of need a snack. This problem is really bothering me, but I feel like I'm stuck. I don't know what else to do with it right now, and I'm getting too tired to like really think about it. I think this might just be a good place to call it. Let me save this before I forget. Okay, let's before we wrap it up, let's respond to chat. In popular vote, it's a two-candidate system in rank choice. You're just adding more candidates if you're talking about the way that they're tallied the same, they're mathematically the same pattern. Getting more sectarianism. Popular vote, you're concentrating the population on two choices. Oh, that's fair, Sock now, but I don't think that's as shocking of a thing as you made it sound initially. Like a primary vote and then a narrowing down to two choices is more or less mathematically the same as ranked choice. I I I would think there's still a slight difference there, but I don't know. Have I heard about Benedict Gross? I didn't know he passed away as chair at Harvard. He also had a YouTube series on undergrad algebra. He passed last year. I did not know about him. Sorry to hear that. But like I said, I do want to wrap things up because I'm getting tired of thinking. reason why I say it's controversial is because people have a presumption they're somehow getting something different from ranked choice. It is actually different. Especially when parties are involved, I think. But yeah, I don't know. Oh, you guys won't be able to hear the music anymore. Oh well. That is gonna be the end of it for me. I'm gonna get the YouTube stream off here. I'm sure to look for a raid. People on YouTube, thank you.